Hi everyone. In this video, we're going to talk about the top key system design problem. It's also called heavy hitters problem. What it means is that you have to design a system that will compute the top key items based on a large amount of data coming our way. So think about getting the top key used tags on Twitter, or computing the top 15 most viewed videos on YouTube, or listen songs on Spotify. Additional, they want to have the data in the real time. So you want to know the top key items in the last minute, hour, day, possibly week, months, or a year. You can use different techniques to implement this functionality. In this video, we're going to talk about the most popular ways to go about it. We're going to talk about the lambda architecture, where we'll have two different flows. One is for the real-time aggregates, and the other one is for the batch aggregates. We'll also touch base on the data structures like main count sketch data structure that will compute the real time. And when we talk about the batch, we'll talk about a different way we can aggregate and compute the counts of specific events, as well as different mappages job that can compute the top key items, in advance how we can aggregate and reconcile the real-time aggregates with the batch aggregates and provide the top key items to our client based on the time frame. First, as usual, we're going to look at the high-level design, and then they're going to review the specific components in more depth. So as you can see on this diagram, it all starts in the API level. This is an interface that we provide to our clients so they can submit different types of events and then be able to retrieve the top key items for a specific time frame. Those events go through the API gateway and then get pushed to our distribute message queue. This is an entry point that distributes to influence of messages that other services push to us from the further processing inside our system. So we'll have two pipelines here. The first one is going to be real time, and the second one is a batch pipeline. So let's review the real time one first. As you can see, our implementation of the real time pipeline is going to be based on the countenance sketch. This is a specific data structure that we're going to review a little bit later, but essentially what it does, it computes the frequency of every single event coming our way. In our case, just assume that we'll have multiple servers. There's going to be a pool of servers that will maintain in memory the state of the data structure. And as the events coming in and consumed from the queue, we'll be updating data structure based on the specific server. In our case, our queue is going to be partitioned, as well as we will have multiple servers of the count min sketch. You can think about it that we might have, let's say, 100 partitions of the queue, and then 10 or 20 consumers that will be assigned to consume from the specific partitions of the queue, and then all the data will be stored into that specific server memory into the count min data structure. So we'll have 10 different servers that will maintain independent data structures that will compute the count of every single event. All those servers every minute going to be pushing that state from the memory to the count min aggregator. So count min aggregator, you can think about it as a pool of servers, again, for high availability, that would receive state from all these different countenance sketches and then aggregate it. In this case, they probably want to have active-passive architecture just so we can have a single aggregator. And then in case it goes down, we have a passive standby replica that can take over the aggregator. But the goal here is that every minute we'll be receiving a lot of different data that will need to be aggregated into the single count min table and then pushed to the real-time storage that, in our case, can be implemented either SQL or NoSQL. We're going to review it later, as well as push this 1-minute state to our top key service that will be responsible for serving top key items to the external client. So this is how we're going to compute the real-time aggregates, and assuming that the granularity is going to be 1 minute. We'll have a lot of 1-minute aggregates into storage then can be consumed by the top tier service to provide a top key item for a longer than 1 minute period. So this is how we will be able to provide the real-time top key items to our clients. When I say real-time, they can think about it with granularity from 1 minute to 1 hour or 1 day. Now let's talk about the batch flow. In our case, we'll continue thence from the main queue and partition aggregator. It will receive events from multiple partitions of the queue that assign to the specific instance, and then compute the count of every single event. In our case, we can consume for 1 minute, for instance, and store the 1 minute aggregates in the memory and then dump them to the file system. Then we'll have multiple MapReduce jobs that will read those aggregates, those counts of the specific events from the distribute file system. Then those aggregates can be read by the MapReduce job. In our case, it can be count MapReduce or top K MapReduce jobs. So we're going to pull all the aggregates from different partitions from the distributed file system and then aggregate them and store in the batch aggregate storage. So when I say batch aggregate storage, since it's going to be a lot of data and our MapReduce jobs are not going to be fast, we won't be able to create 1 minute aggregates. So we can think about 1 hour aggregates. So they'll receive the data from the queue, storing those 1 minute aggregates to the distributed file system. And then every hour, for instance, we'll have a batch job that would get all these aggregates, aggregate them all, and store into the storage as an hourly aggregate. So we'll have all the events with counts for the whole hour. Now, as a result of it, we have two different databases. One database stores 1 minute aggregates, so every event is partitioned by 1 minute, and then the second database that maintains the hourly aggregates for every single event. Then our top tier service can just pull aggregates for either real time or the batch time sequence database and compute the top key items and provide back to the client. Now let's briefly talk about the min count sketch data structure and how it works. As you can see on this diagram, we have multiple events, which are A, B, C, D, E, coming into our system. And we have a min count sketch data structure, which is a two-dimensional array or a table that is stored in memory, and it has a fixed size. So for every single row, we have a separate hash function that is applied to our value. So as we receive an event A, for instance, we have three different hash functions applied to this event, and then the value is stored in one of the columns in this 2D array. So for every single event, we'll have three values stored into three different rows of this table. If we do this for every single event, we'll also have conflicts because two different events can be mapped into the same cell. So that might happen, and the way the data structure works is that when we want to get the value of the specific event, we get the minimal value across all the hash functions. So if we want to, for instance, get a value of event A, we're going to look at three different rows for every single hash function and get the minimum value of that event. This way, if a specific cell had a conflict with another event and has a bigger value, that value is going to be ignored and the minimum value of that specific event will be returned to the client. This is a simple overview of how min count event sketch works. It also worth mentioning that this is the probabilistic data structure. It doesn't guarantee that the frequency of every single event is going to be accurate because it's still possible that two different events get a map into the same cells and their value and the value of the specific event will be inaccurate and way larger than it was. But if we have the big enough table, the probability of inaccurate event gets smaller and smaller. So this is a matter of how much memory we want to give to this table and how big we want to have it in memory, comparing to the different number of events coming into our system. The bigger the table, the less chances to have an inaccurate value for the specific events. Now let's look in our original design in more details. As we discussed before, all the events go through the API gateway, and end up at the distributed message system. What happens since messaging system is distributed and have multiple shards, it means that the same type of event can't end up on different partitions and be aggregated separately. So you can see that we have multiple min count sketch servers that maintain those aggregates in memory. And the same event, event A, for instance, exists on both servers. Those events maintained on the min count sketch servers for 1 minute, then they get sent to the reducer service and refresh its state. So they start over again. This way, we can maintain the servers only with 1 minute granularity. And in case the server goes down or that it is inaccurate, we have very low impact. The reducer service receives all those states from the servers, aggregates them into the single two-dimensional array, and then stores them into the real-time storage where it's partitioned by a minute. Now we have a time series database that collects all the events, aggregates them, and stores in the database where it's partitioned by time and specific value that the data is aggregated by. In our case, it can be either tag or it could be multiple dimensions like country, city, and tag, for instance. The benefit of this design is that our min count sketch servers and reducer service are almost stateless. They maintain a very low state of 1 minute time frame. So if we lose some of them, there is going to be impact, but it's likely not going to be very noticeable. And the real-time storage can serve those 1 minute aggregates by different dimensions to our top K service that will maintain a top K items for a specific dimension and specific events. Now let's look at more details on our batch pipeline. And in the original design I talked about in the beginning, we have a centralized queue that we've discussed already, which is partitioned. And then we have partition aggregator. So the idea here is that events of the same time will arrive from different partitions, as we discussed before. And then we'll have partition aggregator that will consume data from the specific Kafka partitions and aggregate those partitions locally and then store onto a distributed file system. Those events will be consumed by the MapReduce job and then aggregated across multiple partitions into the single value for a single event type. With this design, we allow events of the same type go onto different Kafka partitions, which means we optimize for event even distribution across all the partitions, and then extra processing right after. And we guarantee that there won't be any hot partitions on the Kafka, because the data is going to be evenly and randomly distributed across multiple partitions. But we can also go with a different design, where we add an extra step of pre-processing the events and making sure that events of the same type end up on the same partition. This way, as you can see in the diagram, we have a data partitioner that consumes events from the main Kafka queue, and then it partitions them based on the hash of the event, which means events of the same type will go into the same Kafka partition. And then the further processing will be simplified because we won't have the same type of event spread across multiple partitions. So the MapReduce job will just have to aggregate all the frequencies of the events into the single view and store them into the database. It won't need to shuffle the data and aggregate partial aggregates into the total aggregate. So this way, we simplified the work of the MapReduce job, because now it won't need to aggregate partial aggregates across different partitions, which involves data shuffling and sending across the network. All it has to do is get all the aggregates and then collect them into the single view and dump them into the database. But this approach has its own trade-offs, because by throwing all the events of the same time to the same partition, we have a risk of partition getting hot. What if there is specific tag or video or whatever the event is that is very frequent, and we'll have 100 or 1,000 times more of these specific events than all others? This way, we'll need to deal with repartitioning the data or making sure that this specific partition is somehow split, because if the partition gets too big, we'll be forced to split it into multiple partitions, and that will cause multiple partial aggregates stored in our distributed file storage. So this way, we dramatically simplified the post-processing of our aggregates, because almost every single aggregate is going to be final, and we will have just probably a few or none of the partial aggregates. But at the same time, we add the risk of getting hot partitions and be forced to split those partitions into multiple. And again, if we split them, we will still have those partial aggregates in the distributed file system, but we'll have way less of them than if we went with the first approach. So this is the design of the batch pipeline and multiple ways to implement it. Few things we didn't cover here is how we're going to cache the data, what the database schema is going to be like for the real-time aggregates and batch aggregates, as well as there are a few more approaches you can implement the real-time or batch processing. If you found this video useful, make sure you like this video and subscribe, and I'll see you in the next one. Bye.